Hi everybody. So in this video we're going to look at proving statements involving matrices using the method of proof by induction. So first up we'll start with a basis where we prove that our matrix holds true for the initial case, usually when n equals 1, and this sets the groundwork for the rest of the proof. And next we'll move on to the assumption stage where we assume that what we're trying to prove holds true for a certain case, say when n equals k. It's like saying, if it works for this step, maybe it works for the next one too. And then we'll move on to the induction stage, where we'll show that if our statement holds true for n equals k, then it must be true for n equals k plus 1. This is the heart of a proof, where we really see the power of induction. And finally, we'll wrap it up with a conclusion, where we'll show that since our statement holds true for the first case, and every case after that, it's true for all natural numbers n. So we'll start with example 1, where we've been asked to use mathematical induction to prove that this matrix to a power of n is equal to this 2 by 2 matrix for all positive integers n. So the first thing we need to think about is the basis, and this is when we're saying that n equals 1. So we'll substitute 1 into here. So we get 1, 0, 2, 1 to a power of 1 is equal to, then we'll substitute n equals 1 in here as well. And this will give us 1, 0, 2 times 1, and 1. So you can see then that the left-hand side is equal to the right-hand side. So this means it's true when n equals 1. So now we go on to our assumption stage, where we assume it's true for n equals k. So we have 1, 0, 2, 1 to the power of k. We're assuming it's true for 1, 0, and then we replace this n with k, so we get 2k and 1. And then for our induction stage, this is when we say n equals k plus 1. So if we substitute k plus 1 into here, we get 1, 0, 2, 1 to the power of k plus 1. If this holds true, will be equal to 1, 0, 2 lots of n, which is k plus 1, and then 1. So this is like our aim. This is what we're trying to prove. And we can work out n to the power of k plus 1 as the matrix raised to the power of k multiplied by the matrix raised to the power of 1. Because when we multiply this by this matrix, using the rules of indices, we can just add the two powers, which will give us to the power of k plus 1. But we've assumed that this matrix is equal to this matrix. And we've shown that this matrix is equal to this one. So we can rewrite this as 1, 0, 2k, 1, multiplied by 1, 0, 2, 1. Now all we have to do is to work out the product of these 2 by 2 matrices. So we'll multiply the first row by the first column. So we get 1 times 1 plus 2k times 0, which gives us 1. Then we'll multiply the first row by the second column. So we get 1 times 2 and 2k times 1. So this gives us 2 plus 2k. Then the second row times the first column, 1 times 0 plus 1 times 0, which gives us 0. And then the second row times the second column, 0 times 2 and 1 times 1, which gives us 1. But if we go back to what we're trying to show, this, well, we can factorize 2 plus 2k. So this will be equal to 1, 0, and then 2 lots of 1 plus k, and 1. So we have what we're trying to show here. So for our fourth stage, the conclusion, we say, if it is true for n equals 1, and true for n equals k plus 1, when assumed true for n equals k, then it must be true for all positive integers n. Okay? So I hope that's given you an idea on the basics of proving statements involving matrices. In example 2, we're going to look at a slightly more difficult example. Okay, so in example 2, we've been told that the matrix M is a 2 by 2 matrix, 2, 3, 0, 1, and we've been asked to prove by induction that this matrix, when raised to the power of n, gives us this for all positive integers n. So do you want to try this question yourself using these 4 stages? You can pause the video, and when you come back, we'll go through the work solution. Okay, so welcome back if you had a go. So we'll begin by writing our basis, and this is when we let n equal 1. So we've got n to the 1 will equal, we'll substitute 1 in here and here. So 2 to the 1, 0, and then 3 lots of 2 to the 1 minus 1, and then 1. We can simplify this as 2 to the 1 is just 2. 2 to the 1 minus 1 is 2 take away 1, so 1 times 3 just gives us 3, and then the 1. So we can see that n to the 1 is exactly the same as what we have here. So we've shown that this is true when n equals 1. Now for our assumption, we assume this is true when n equals k. So we'll substitute k into here and each of these. So we get m to the k is equal to 2 to the k, 0, lots of 3, 2 to the k minus 1, 1, and we'll close that bracket. Okay, so for our induction phase, now we're going to say that n is equal to k plus 1. So at this point, it's really important to write down what we're trying to show. And this is m to the k plus 1 will equal, and I'm going to substitute k plus 1 into each of these. So we get 2 to the k plus 1, 0, 3 lots of 2 to the k plus 1 minus 1, 1, and we'll close that bracket. So as we work through the next stage, this is what we're trying to show. So the working will follow m to the k plus 1 will equal m to the k multiplied by m to the 1. And because these bases are the same, we can add these powers and we'll get what we're trying to show. And we can use what we've assumed here, m to the k. We can use this matrix. And then m to 1, we can use this matrix. So we'll get m to the k multiplied by m to the 1. And now we can multiply these two matrices together. So we'll multiply the first row by the first column. 2 to the k times 2, and this times 0, will give us 2 lots of 2 to the k. The second row times the first column, 2 times 0, add 1 times 0. The first row times the second column will give us 3 lots of 2 to the k, plus this times 1. So 3 to the 2k minus 1. And then our second row times our second column, 0 times 3 added to 1 times 1. And we're just going to think a bit more about what's happening here, because we need to make this look like what we've said here. So I'm going to start by expanding out this bracket. So we have 3 lots of 2 to the k, plus another 3 lots of 2 to the k, minus 3. We can add these two together, and we get 6 lots of 2 to the k, minus 3. And then we can see up here, we need to factor out the 3. So this will give us 3 lots of 2 multiplied by 2 to the k minus 1. And we can simplify this by adding these two powers together. So we get 3 lots of 2 to the k plus 1 minus 1. So I'm just going to tidy this up a little bit. We'll rub this out and we'll replace it with a simplified version. So now for our conclusion, we'll say this is true for n equals 1. It's also true for n equals k plus 1, when assumed true for n equals k. So therefore, it is true for all positive integers n. Okay? Well, thank you very much for watching. I hope you found that useful. If you did find that helpful, please like and subscribe. And you can download the full lesson and worksheet from my website, mrmathematics.com. There's a link in the description below. Thanks again and take care.